Hi, welcome to Amazon Summer School. I am Ahmad Sanin, and I am an applied scientist here at Central Machine Learning team at Amazon. So in this session, we'll be covering the third part of sequence learning. So here, so far, we have learned about some text representations, some encoder decoder models, self-attentions, etc. So here we will see where all of these concepts come together. So we'll be covering some of the architectures like transformer models, BERT, etc. So we have seen before, like, so the first step whenever we get a text access as an input is converting it into tokens. So the question comes like, so how do we turn a raw text into these tokens, like into these integers, so that a neural network can consume? So what is that thought process we should be having? What type of tokenizations which we'll be using? So that intuition behind uh, these different steps is what we will be looking at in this particular part of the session. Now, let's assume. So here we understood that the model sees numbers and not text. Now, as I was saying, the important question we should be asking is, how will we split a sentence into some sets of numbers? So first thing comes in our mind is, say I have a sentence. Let's split based on the spaces between. So here the sentence is the cat sat. So how will I split? I'll say like the is a token, cat is another token, sat is another token. So now based on that, I'll do the split. So here I have three tokens. Now, so this is a very obvious way of splitting, right? But the question is it the best way of splitting it? So are we going to face any challenges if we split our words, our sentence based on spaces? Now, I have pasted a few questions here. So each of the questions, when we go through, just take some time to think through, like, hey, is it a challenge? Like, or should we come up with a different method, or whatever method we are having so far, is it going to solve it? So the first question is like, so what happens when a word shows up that wasn't in the training data? So we have never seen that word. A new word was invented, or a product name or something else is coming. Now, what will we do? Like, which token will we giving? So if we split on spaces, it's like whatever word is gonna come, we are expecting us to know it way beforehand, so that we will predefine tokens for each of these. Right. Now, let's come back and see this scenario where we haven't seen that word at all. Then what will be the token for that? Yeah. So if the vocabulary have never seen a word, always every time we can give an unknown token. So there will be a special token, we fix it for unknown words. So this is called out of vocabulary words. Now, what happens like a new name comes, a product or code or different slang coming, there will be lots of unknown words. Is it a good thing to do? Because our language need to understand, even when an unknown word comes, should not be like always unknown, right? It should get some sense of this word. Now, what is the next problem which can happen? What about a small typing? See, when I type, I make tons of typing mistakes. So what about these small typing errors? Then in that case, uh, what uh, what should be the token for that? So let's say I have, instead of playing, I write, uh, it looks playing, but there I made a small typing error here. So in this case, are we expecting you to put an unknown token here, or somehow our model should be able to understand, a, this is a typing mistake, right? So this is another issue. Now, the other issue is, what if the vocabulary size is too huge? So if you take all the words in English and every other language possible, you have all the possible slangs, etc. So we'll be having a very huge vocabulary size, which we won't be able to keep track of. That might increase some of our computations. Now, see, we understood what all are the some of the problems which we might be facing if we use space as a split. Now, what is the next very intuitive solution? I can take character wise, right? So that is a next thing which is space is not working. Let's say I take character wise. For example, I have a word playing. I'll say each of these letters like P, L, A, each of these I can consider as a token. Now here, what will happen? See, one issue is solved. Like even if we make a spelling mistake or even a new word comes, this is going to take care of it, right? But what is the problem with this is, see, even just this playing one word, it's what like one, two, it's seven, no, it's eight, or no, not eight, seven tokens, right? So when we have a huge sentence, like sentence with hundreds of words, the number of tokens will be very huge. So when we use LLMs, we will be able, we are out of tokens. So the cost is based on the tokens. So we understand that more the number of tokens, it's not good for us. Now, you see here, due to this, we'll be getting order of n square computations. So our computations will go exponentially. So which is not something which we want. Right. The other thing is the probability when we make a prediction. See, just P don't have a meaning associated to it. When playing comes, that's when the entire meaning comes. So the probability of what word we are predicting, instead of word, like if we are predicting a single character, that probability loses inherent meaning. Right. And it's also difficult to figure out the long range dependencies. So even this method doesn't work. Then what is something which comes in between? So we told us splitting with spaces, keeping the words as it is. There are problems. Now splitting character-wise, we have problems. Now, what is the next solution which might be coming into your mind? Why don't we do a subword tokenization? So instead of making each character a token or keeping the entire word a token, why don't we group characters? Let's say I can say that play as one token and ing as one token. So this is called a subword tokenization. So instead of keeping the entire word, we grew the most common occurring words, like frequent words says together, and rare words are split into pieces. Right. Now the question comes: is it solving all our problems, which we have seen before? When a spelling, so here you can see the playing, how we are going to split, etc. We are going to see it in the future slides. But just assume like I'm splitting like this. So playing, I can split like this. Tokenization, I can split it in this way, or this GX, GZ, like some random word. In this case, it will split into tokens. So when a new word comes, it will be able to split. When a spelling mistake is there, it will be able to split. So all our problems are solved. And even the number of tokens, like, so we don't need to know the entire words in the vocabulary because we are grouping things into together, right? So the number of tokens or the vocabulary, not the tokens, the vocabulary size will come down. At the same time, the token number of token size also coming down compared to our character wise split. Now we can use different methods to split a sentence into subword tokens. So there are methods like byte pair encoding, word piece, and unigram. So we'll be seeing each one of these and how it's splitting the words into two subwords. So let's move into the first method, like which is byte pair encoding. So how it's done. So let's see here. Now let's assume. So let's see this with a example. So it will be easy for us to understand what is really happening in byte pair encoding. So the example which we are taking here is, I'm saying that I have, so there is lots of sentences. So I have a big corpus of training data. So in which I'm just taking a hypothetical example for easy understanding and easy visualization. I have this term hug 10 times, bug 5 times, pun 12 times, and bun 4 times, and hugs 5 times. So this is These are the distribution of some words in it. Now, using this, I'm going to demonstrate how this byte pair encoding is done. Now, and then with the same logic, you can extend to n number of words, right? So here, let's see. Yeah. So if you see here, so the current split, what is happening? We have H, U, G. We have not combined everything. We have kept everything character wise. Now, let's see how many characters we can combine. Even if you take this UG pair, right? So UG, you can see that this U plus G, there is 20 times occurring. 10 from here, 5 from here, and another 5 from here, 20 times. Similarly, each of these pair, their counts has been given here. Now, logically, the first uh, characters which we combine together is U and G. So what we will do, instead of keeping this U and G two separate character tokens, we combine it and say it as a single token, right? So this is what we did. So all UG, I combined it and kept it as a single token. Rest all as are kept as it is. Now I'm looking at the second pair. Now I can see that this U plus N is coming 16 times and H plus UG is 15 times. So next logical decision is I'll combine this U plus N. So what I'll do, I'll go ahead and I'll combine this U plus N. So this UG is combined before, UN is combined now, yeah, and rest all are kept as it is. Now we will keep merging till we reach a state there where we don't have a very frequent occurring pairs. So this is the byte pair encoding. Like we find these pairs and we will look at the frequencies and we will decide whether to merge them or not. Now let's see, let's complete the sequence anyway. So next merge we go, I got hug is the something which merge because that's coming 15 times. Then P plus UN. So similarly, if we keep merging everything, at the end, we will get that entire space-based tokenization we had, right? The entire word. We'll be getting that. So what we'll be interested in is that intermediate stage where we take care of almost all the frequent occurring pairs. I hope it's clear now. What is byte pair encoding? It's clear. Now let's move to the next section. Yeah. So this is one example. As we can keep giving any word, and based on the previous tokens, it will be bringing us tokens. I hope it's clear. So we don't need to spend much time here. Let's move into the next session. Yeah. Now we'll be looking at this word piece. How this particular tokenization is done. Right. Now in the previous case, we looked at the total number of times these two characters are coming together. But whereas in the word piece, what we are more interested in is not the number of times it came together, but what is the frequency of times it came together. I'll clarify that. So for example, you take these terms like G and S. So in our previous case, if when we look back and check G and S, so let's go back. So G and S were occurring 5 times, right? So, and if I take just G and just S, how many times it's there? So G is there 10, 15, close to 20 times, and just S is there 5 times. So then what we do, we take a score, frequency of A comma B coming together, divided by frequency of A and frequency of B, and we will see which score is highest, and that two tokens we will combine. So here we can see that G and S score is highest. We will combine it. Then we will look for the second. Then we look for the third, and then we keep on. Then we keep on combining it. Right. So based on byte pair encoding, if we merge, U plus G will be merged first. Based on word piece, if we merge, G plus S will be merged first. So Why the difference? So dividing by the two piece frequencies favors the pieces that are individually rare but keep showing up together. So these characters might be individually rare, but whenever they come, they are coming together. So logically, it makes sense, right? So that is something we need to combine together. Now let's see the last unigram sentence piece, right? So here, what we are doing is, so every word in the vocabulary carries a probability. Now, to tokenize a word, what does the model do? The model look at all the ways it could be split and keeps the one with the highest combined probability. So here you can see like it look at all the splits possible and it takes the highest probability. That's how the split will be made. So in this case, dogs and S will be having the highest probability, and that is a split we'll be keeping. Yeah. So we have learned these three: byte pair encoding, word pieces, and unigram or sentence piece, right? So let's try to revise this concept once. So the direction in which we go in byte pair encoding, it's bottom up. So we split it into characters, then we combine. Word piece also bottom up. We split it into characters, then we combine. Unigram or sentence piece, we come from top to down. It's top to down. We start from the word, but then we start splitting and we'll come down. So the selection rule is most frequent pair. This is highest score and max likelihood split, right? Yeah. Now out of vocabulary, there is none. In word piece, unknown is possible, and in unigram also it will be none. And which are the top models which use it? Byte pair encoding is being used by GPT, and this section is like what we should be remembering is why we are using subwords and the mechanism we followed, and the three different subword tokenizations which we used. Now, let's move into the transformer architecture. So we have already seen attention, what is self-attention in the previous session. But again, we will try to visualize this once more for the complete understanding. Right. So this is a high-level overview which you are seeing here. So we will go into details inside each modules in the upcoming slide. But in high level, a sentence will be coming. We'll be converting it into embeddings. Then there will be also positional embeddings. Then all of these will go through our transformer blocks. Then we'll be having a softmax at the end, and we'll be predicting the next word. So this is what that entire transformer architecture is doing. So we will see each of these components in detail. Right. So this is also a bird's eye view. We are not going very deep into each of the concept, which we will do in the later slide, but let's have a bird's eye view first. So this sentence is coming, the cat sat. First, I'm tokenizing. So here we are not using any byte pair tokenization or something, or maybe this is how it happens when we do a byte pair tokenization. But here, just assume we are just doing a space by split. So the cat sat, we are taking the cat and sat. So once we have these tokens, we convert it into embeddings. So the first row you are seeing is the embedding for then the second is for cat, and the third is for sat. So here the embedding dimension is 4, just for easy visualization. Then we need a positional encoding. So what is exactly a positional encoding? We'll come on a later stage. But here, this is to understand like which position the word is, like which position the is coming, or which position the SAT is there. So we have this positional embedding. This is a positional embedding, and we'll add this token embedding with the positional embedding, and we get the final embedding, which we are going to pass it to our transformer block. Now we have a transformer block with lots of things happening. Like there is this residual connection is there, feed forward layer is there, there is a multi-head attention layer. There are lots of things happening inside it. So and there can be n such transformer blocks. So once we get the output from it, we take a logic softmax, and here we'll be getting what is the distribution of probability of the next word, which we can predict, and based on we'll be choosing what is going to be the next word. Now we will see this entire architecture in pieces. So to get a complete understanding, it's always good to understand the dimensions of each matrix or what are these terms means. So here n means the number of tokens in the sequence. So in that sequence, what is the number of tokens which we are passing? It can be 10, 20, anything. So that is n. And D is the size of each token vector. So each token, that embedding size is what we call D. And H is number of attention heads. So here we have seen, like when we were going through the self-attention module, you might have seen how multi-head attention, self-attention works. So here, how many heads are there? That is represented by H. Now DK, this is size of each head. So total size should be D. So if H head is there, especially the size of each head will be D by H. Now DFF, this is feed forward layer, like there will be hidden fully connected layer, right? So what is the dimension of that? That is DFF, D fully connected. Then N, like how many transformer blocks are stacked together. So it can be multiple transformer blocks stacked together. So how many such transformer blocks are stacked together? Then V, it's a vocabulary size. Right. Now, so here, this is our running example. So the cat sat, we have this matrix created. So here n is 3, like a number of tokens in this sequence is 3. So we have 3 and the dimension is d. So this is d, 4. So d is 4 and n is 3. And in the example we are going to show what I'm expecting, h should be 2, h will be 2, like there will be 2 heads, and dk is 2, dff is 8, and n is 6. Yeah. Yes. Now, before moving into the uh, visualization of how the transformer network works, let's understand why we need positional embedding, positional encoding. For example, so here I have two sentences, right? Or like dog bites man, and the other is man bites dog. So in these both places, if we don't have a positional embedding, what will be the embedding of a dog in A and what is the embedding of dog in B? It will be the same. Now, how will we know that? Did the dog bite the man or the man bite the dog? Right. So this is a reason why where exactly this sentence is, or at least a relative position of this sentence, is very important. Now, once we have these relative positions, I can add it, and then I'll be getting a position aware embedding of my token. Now, let's see different types of positional encoding. So here, what we want to do is we need to capture the position of that particular token. So there are mainly two types, like which is absolute and relative. So let's look at the absolute one. So one of the common positional embedding people use is, one is this sinusoidal positional embedding. So where, let's say we have D dimension, and each of these, like assume that this position is 0, position 1, position 2, etc. So this 2i will be even positions, and 2i plus 1 will be the odd positions. So we define these positions with respect to this sine and this cos equation. So this is which position the word is, and by power 10,000 power 2i by d. So this will give us the positional sinusoidal positional embedding. And here you can see, like, when I change this position. So when I change this position, how this is changing, like, so if the dimension is low, like when the dimension is zero, it moves faster. And when the dimension increases, it moves slower. Now, the other type of absolute position encoding is we don't define, like, here, like sine or cos, we don't define these things. Rather, we let the model learn. So we start with some random weights and we let the model learn these embeddings. So in this way, we are saying that based on the sentences, based on the meaning with large corpus of data, we let the model learn this positional embeddings. That is another way. Then there is relative positional embedding. So far we have seen absolute positional embedding. Like whatever be the sentence or whatever be the word, that first position will be having one particular embedding, second position will be having another embedding, third position having another embedding, etc. Now the relative is, see, we are not worried about the absolute positions. Rather, we are worried about the relative positions. From word A to the word B, what is the relative position is. Then based on that, we formulate a position embedding. Now, some of the latest positional embeddings are this rope and alibi. So here, one thing we all need to think is that, see, embedding has its own meaning. So word embeddings has its own meaning, right? So embedding of a word means something. Now, the moment I add something to it, there's a possibility that that meaning might be lost. So even though we are saying that this is position infused embedding, but the real word meaning might be lost. So instead of adding positional embedding to the real embedding itself, can we bring some intuitive way of adding this positional embedding? So there is one method called this rotatory positional embedding. So here, what they are doing is they bring this rotation in the query and key metrics. And then we have this alibi. So here, what it does is based on the position, it does a scaling, the strengthening. There will be a learn parameter which strengthens these vectors based on the positioning. So in both these methods, what we are trying to do is we are not adding a positional embedding along with the word embeddings. Yeah. So now this positional embedding is clear. Now let's move into this transformer architecture itself. So in the transformer block, let's say we have this embedding and positional embedding. And when we move to this transformer architecture, we have this multi-head attention layer, layer normalization layer, feed forward layer, and some of these layers are connected by residual networks. We will see these things in action now. So before seeing the example, let's understand like how just a high level overview on self attentions. We have already seen it, but let's say recap of that concept. So given a vector array in embedding, we do a multiplication of then embedding with this query key and value vector, and the attention score is calculated based on this particular equation, right? Now we will see all these things. So don't worry about this multiplication and how these happening. We will see a example based on real matrix multiplications. Now let's look at an example, like how starting from an input, how this attention mechanism happens, like how different stages of this transformer layer. So here you can see like we are starting with this sentence, the cat sat. And the dimension we are having is, now we have n is equal to 3 and the dimension of each embedding is 4. So here we are taking, this is for each of these word, the row represents that particular embedding. Now let's go to the next step. So the next step is whatever this input is, we multiply with query, key, and value metrics. So here our number of heads we are assuming is 2. So this is one head multiplication happening, and at the end we assume that there is another head is also there, and we concatenate. So here first multiplication happened with the query matrix, then with the key matrix, then with the value matrix. So once we have this query, key, and value matrices, what we will do is we need to do query dot key transpose. So this is whatever query we had, we are multiplying with the key transpose, and we are getting the row scores. So once we have the scores, see one thing we need to do, we need to scale it down. So we divide the scores by root of dimensions, and the reason we are doing is otherwise the variance will be too high. Like so, we need to bring it down in that 0 to 1 range. So that's the reason why we are dividing it by root of dimensions. Yeah. And once we have that scaled scores, we need to take softmax of that scaled score. Then we'll be getting this attention scores. So we took a softmax. So each row wise, we'll be taking a softmax. Yeah. Now, once we have this attention, what we will do, we'll multiply with the value matrix which we had before. Then we will get our final output, right? So this is the attention. This is the output from that attention layer. After final multiplication with the value matrix. Now what? Like, see, once we have this is for a single head, right? So similarly, we will be getting for other heads too. In our case, we have two heads. So if you see, like we have two heads, so we got output from both the heads. We'll concatenate those output, and then there is a projection matrix with which we'll multiply. Even these projection weights are learned, which will multiply. We will get our final output. Right. Now, once that attention layer is done, what we will do here is there is I have shown you, right? There is this residual layers, like so from that input we will again add it to this output. So that is this residual connections happening. That post residual layer we will have a normalization layer. Right. Yeah. So you might have seen multiple normalizations happening. So in this here we are using this layer now. So you might have seen that there is batch norm, layer norm, multiple types of normalization. So in our case, we are going with layer now. So the way it happens is we take each of these rows, then we normalize across this dimension. That's what we are doing. The reason we are not using a batch norm, there are multiple reasons we can say. One, uh, the size, that input size is not fixed. The second reason can be like the meaning is not across the columns, it's across the rows. Like so, that entire word has a meaning. So if we normalize it across different input, that inherent meaning might be lost. So there can be multiple. There are multiple reasons why we go with layer norm. Now, once that normalization is done, now we have this fully connected layer. So in the fully connected layer, what happens? Like we expand it, then we again bring back to the same dimension. Let's say we start with dimension 4. So here, if we see the dimension is 4, if we start with the dimension 4, we expand it, then we bring back to dimension 4 itself. And this is normal neural network multiplication, whatever basic neural networks we are having, the same thing we are using here. The difference here is in the activation function we use is GELU. And GELU is this is CDF of standard normal distribution. Now the only difference this with the ReLU here is when it's closer to 0, this is a little more smooth. It won't be having a very strict boundary. So it will be little more smooth. Like so towards the end, like when x gets larger, it behaves like ReLU only. But when it is closer to zero, it won't directly go to zero. Rather, it's smooth, like it's slowly transition to zero. Now let's see this fully connected layer in action. So we have this x, we have this weights, we multiply it, we'll get this. This is a hidden state. Now this hidden state, we apply this GLU, then we get that final feed forward layer output. Now this output we will again multiply with x residual. This residual connection is happening. Then we will get our final output. Now we have seen this transformer layer happening. Like, see what is happening in one transformer block. So in that one transformer block, we were having self-attentions, feed forward network, normalization is happening. Then also this residual connection is there. So we have seen that. Now, if you take that entire transformer model, we have this encoder and decoder part. Now, what is the difference? So both has this transformer blocks. Now, what is the difference of these blocks in these two stages? So one, we should understand that encoder understands the input. Like it has the context of the entire input, that whole input will be going in. Decoder here, it won't be able to see the future inputs. So it is an autoregressive model. It has context of the previous input, but it doesn't have the context of the past input. So how are we changing the encoder, transformer part in the decoder? So if you see in when we were discussing this transformer block, you have seen the scores. Like after multiplying this query into K transpose, we got the scores. So there we kept the scores based on all the inputs, right? Now in decoder stage, what happens? Like whenever the comes, it won't be able to see cat and sat, or the cat stage won't be able to, so it won't be able to see the future tokens. So we need to remove, when we take that softmax, we should not be taking it. So generally we should convert them to zero. So here you can see when we take this softmax, the other things are assumed to be zero. Then how is it achieved? So the way it is achieved is in this diagonal elements, we give all the elements as negative infinity. And now whenever we take the softmax, that is automatically will turn into zero. So that's how it's been achieved. Yeah. Now, so this is one thing. So in the decoder stage, there is this one thing. We have this masked attention. So we have this masked attention. One diagonal will be masked. The other thing in the decoder, there is something called cross attention. So what we will do here is we will take the key and the value from the encoder. Then query will be taken from the decoder itself, but the key and the value will be coming from the encoder. Then we'll be having this cross multi-attention layer. So these are the two things which is there in the decoder part. We have this masked self-attention. Then there is also this cross attention. Now let's see the overall thing, the full diagram, like whatever we have discussed so far, we can see that entire full diagram. What happens is the input embedding is coming. There will be multiple transformer blocks with multi-head attentions. Add and norm means this is residual connection, like normalization, fully connected layer. Then in the decoder also we have similar things, but instead of multi-head, we'll be used masked multi-head attentions. And there is also a cross multi-head attention layer. Yeah. And finally, we will have this linear layer. Then so we will take the softmax, and whatever is the maximum probability coming, we will consider that as a next word prediction. Yeah. Now let's see. So this is the output. Let's say this is the output we are getting from that decoder transformer block. Then we have this word vocabulary size. So this is where that vocabulary size is very important. Like if the vocabulary size is very huge, like every words out there or every new words, we need to add this vocabulary size. This metrics will be very huge. Now we were looking into this byte pair encoding and all those things, right? So that actually brought down the vocabulary size. So now we are multiplying it So here we are just for visualization purpose, we only took 4 as a vocabulary size, not 4, like 6 as the vocabulary size. Now we get it. So when we predict, we got the probabilities, and here the probabilities you can see on is having the highest probability, and we will be setting on as the next word prediction. Now this cycle continues. Once we predict on, the entire cycle continues again till we get that stop word prediction. Now let's see some language models like BERT, GPT, T5, and all. Right. So if you look into language models, there are 3 class of language models. One which is encoder only model, decoder only model, and encoder decoder model. We have seen some of these things, not in action, like some of the concepts behind this. These we have already seen it. Now let's see how the proper pre-training and fine-tuning is done on these models. Right. So generally, like we have plenty of supply for data to pre-train our large language models. So we have all the text corpus out there. So what we do is we hide the next word in GPT types of training. We hide the next word and we try to predict it. And in BERT family, like encoder only models, we hide some words inside or some change some words inside, then try to predict it. Yeah. So this is what we'll be doing. Now, the question coming in our mind is why we need pre-training in the first place, or rather just we have a use case, like we have train input and output. Like, why don't we just go ahead and train it? Why should we spend time understanding the language? So the reason here is like once we have a model which understands the language, it's easy for us to tune to a particular task rather than just training that model for that this particular task. Yeah. Now let's look at high level overview on these different class of models. So here encoder only, it's a bidirectional model. Like it gets the entire word and it has context of both the directions. And the pre-training techniques we use is masked language model, which means like we mask some text in a sentence, some places we mask it and we try to predict it. And it's very good at understanding the language, right? So some of the classic examples like BERT and Robert are some encoder only models. Now in decoder only model, the attention we use is causal. It's a masked causal attentions which we'll be using. And it's an auto-regressive way. We train it auto-regressive way. We try to predict the next word. Yeah. And it's best for generation. The examples are GPT, Llama, and all. Now we have encoder decoder model. It has both. Like it understands the bidirectional attention and the causal masked attention is there, and it's generally used for denoising. It's best for sequence to sequence transformations, and the models are T5 and BART. Right. Now let's go deep into just the encoder only model. We'll take BERT in this case, right? So it's bidirectional. So every token mixes with token on its left and its right. So each token vector is rich with context. So what BERT does is BERT produces representation and it does not generate text. So it produces a representation. Whatever input we give, it produces a representation of that input, right? Now, as I told you, it has the entire context, right? It's bidirectional. Now the question comes is, if it is bidirectional, when we are giving the input, it already knows the entire what is there in left and what is there in right. Now, how are we even training BERT, right? We will see that. So BERT, the input, what we do here is, so we have this input. So we'll be taking, let's say we are taking two sentences, two parts of the sentence. And we'll start with one CLX vector and there is this separation token. So CLS gives a summary of this entire thing. So CLS token embedding has a summary of this entire sentence which we are giving, and separation is to separate two sentences. So there will be token embedding, then segment embedding. Like, is it part of segment A or segment B? So there will be segment embedding, and we also have the positional embedding. and adding these three, we'll be getting the input embedding. So this is the input to the BERT model. Now, at the time of pre-training, what we will do, like we will mask. So two tasks we will do. One is masked language model. So what is it? We will mask one of this word in it. So let's say this is a word. I'll just mask one of it. Now, it won't be always masking. So we'll do these three things. Like 80% of the time, we will do the masking. 10% of the time, we will replace it with a random word, and another 10% of the time, we keep it as it is. And why are we doing it? Because if you always I remove the word, like you always I masked it, what happens is this my entire bird will only be suitable for that particular task. So here the claim is the bird should understand the sentence, right? So even if we replace with a random word, or even if we didn't unchange, even we didn't change the word at all, the bird should be able to understand this. So this is the core idea. And now when we do this mass language prediction, when we predict it, whatever is the word which has the highest probability to be here should be getting the highest probability. Yep. And the second task which we will learn BERT on is the next sentence prediction. So we have two sentences. We will try to predict whether is it the next sentence or it is not the next sentence. So the sentence you take the cat sat, it purred. So this is the next sentence. So whatever prediction we do, should predict that it is the next sentence. The other one, the cats sat, stocks fell. This cannot be a next sentence. So it should say that it's not the next sentence. So to do this, I told you that we have this CLX vector, which has the entire history context, and we'll have a classifier and we'll try to predict it. So that's simple. So BERT, it's trained on, we have this next sentence prediction and master language model, master language prediction. Now, once we pre-train the BERT, we need to fine-tune for our task. Our task can be anything which it can be sentiment analysis, it is NER, QA, so it can be anything. Like so, now how will we fine-tune our BERT on these tasks? So we have this pre-trained BERT. Any sentence is given, we will be getting this CLS vector. Now we can do our new task. It can be a classification, whatever it is. So this has the context. BERT has the understanding of what that sentence is. Now using that, we can perform our own task. And as BERT has been trained on a huge corpus of data, now to fine tune to our use case, we just need very few data points. We don't need an entire very mass corpus of data. Now we are moving into decoder only models. So the models like GPT, Llama, and we have seen what really happens in the decoder part when we were explaining transformers. So similar to it, just understand we'll be giving some way what is the current state of the sentence, and we need to find the next token. So that's all what we are doing in GPT, right? So here we'll be using this causal masked attention, which we have already seen. What the idea here is the word should not see the future words. It's an auto-regressive model. So it will be seeing one word at a time. And given these inputs, so what we are trying to predict here is given all these inputs like x1 to xn, these are, let's say these are n tokens, I need to find the next token. So that is what this GPT or a decoder only model does. Now, how we are doing it, let's see. So again, I'm giving you an overview on what it's happening here. So we start with the input, we multiply with the query key value vectors, then we scale it down, then we take softmax. Before taking we'll be using causal. So before taking softmax, we'll replace it with the negative infinities, right? We have seen it. We know why we are doing it. And once we take and we do the softmax, and after taking the softmax, we multiply with the value vector, we'll get the output. If it is multiple heads, we'll take multiple heads and we will concatenate, and projection matrix, we'll multiply with the projection matrix, right? And uh, yeah, and once this is done, we'll be having this feed forward network and all those things. And let's assume we got that final layer. Now, what are we going to do to that final layer? How are we going to predict what is the next word? That's what we are going to see. Yeah. So here, this H, there's an output from our transformer block. So what we will do, we to get the logics, we multiply with word vocab. Then to that logic vector, we will do this softmax. So this will give us the probabilities of each word occurring. Now here you can see, right? So once when we are looking at it, on is having the highest probability. Now whenever we take a yeah, so here when I randomly sample from this distribution, I'll always be getting on. Right? Now, is that what we really want? Like, so is it should be a very deterministic prediction every time, or do we need varieties of predictions? So this is where the concept like temperature, top K and top P comes. So to this logic, we make few changes, and while sampling also we make few changes so that we end up getting diverse answers. So here, what by temperature we mean is whenever we are doing this exponential in that softmax, we divide this logic logic by a temperature T. And when the temperature changes, so here you can see when the temperature changes, so before when the temperature was zero point 0.5, like this is how you are seeing that mat has the highest probability. Right. Now when I change this, what is happening? Everything like rug, sofa, floor, these things are also getting more probability. So this is what happens in when we change the temperature. Now, when we sample it, there's also possibility it is not just mat, even rug can be picked up because there is no much difference between their probabilities. Now here, see, when we do this, what can be the other problem happens? There might be words which should not be coming there, will be getting huge probabilities, right? So which we don't want, right? So here table is afterwards there might be other words which won't fit into a sentence. So in those cases, what will we do? So there is when this top K comes. So what we will say that we will only look at the top 10 words or top 30 words. That's all. We don't need to worry about any other words. Then we have this top P. Here, I'll give another constraint like that cumulative probability should be of a threshold. For example, if I give the cumulative probability of 0.5 or give it a 0.55, then what happens? Only these two words will be taken. So the moment you take these two words, it's already close 0.5. Then we will take that from these two words, we'll do the sampling. So this is how the combination of this temperature top K and top P works. Now let's see like so we are starting with a prompt the cat sat. We are trying to generate next word, then on the. So this is how it is going like. So what we do, each time we will input this, then we will try to predict the next word. We will try to predict the next word, and whatever process we have seen, every time it will be going through the same process. Now there are concepts like KV caching, etc. So here, some of the computations we'll be redoing it again every time, which we don't have to do it. So instead of doing it every time, we cache it somewhere so that we can reuse it. So that we won't be end up doing extra computation unnecessary. So this will increase the inference speed. This also increase the memory required for inferences. Yeah. Now, once this pre-training is done, then what is next? So I pre-train. Now I should do some task, right? So few things we can do is one is prompting. So pre-training is done. You do prompting with maybe some few short examples. Then it will do your task, like without any fine tuning or anything, it should be able to perform your task. Now the second step is instruction tuning. So you give some instructions and you tune it based on this. So this is an instruction fine tuning will be happening. So here you would again updating the weights, etc., based on your use case. Now we have RLHF, reinforcement learning, human in the loop. So here what happens is based on a feedback and a reward, few final layers of the model will be updated a bit. Now let's see like fine tuning case. So in the instruction fine tuning case, so how this fine tuning is done. So one thing, this assumes this is your entire GPT model. X is going in, Y is coming out. Now, one way of doing here is you can fine tune the entire weights. Like so, you have your own train set. You can update the entire weights. That is one way of doing it, right? So few issues there. One, it might take time. Like the model can be huge, so you want to update the entire weights. It will take time. Now, second, if you think, see, it's learning language, right? It already has an understanding of your language. So is it always a good thing to go ahead and update the entire weights? Right? May not be like you might be updating some learned or overlaying some learned, forgetting some learned languages, right? This is when the next concept comes, which is adapters. So in adapters, what we do, so we have that previous model. So this green part is something I add extra. So I will go ahead and add this adapters layer in between. Then I'll only learn these adapter layer. Rest all I'll fix it. Now, what is the problem here? So here the problem is I'm increasing the weights of the model. Like the model size is going up. Right. Now, is there something else I can do which still makes the model training faster, but won't increase the model weights by too much? That's when this concept of LoRa comes. So in this LoRa, see the entire weights we will be fixing. Now we will have a low rank adaptation of these weights. So here, if you see the entire weights, the model size will be very huge. When we do a low rank approximation, that's a very smaller, very smaller size. Then we will just learn these weights. And here, other idea here is like as the model weights are fixed and we are only keeping these weights, so we can have the root model same for multiple applications. We just have to update this A and B and store this A and B metric somewhere for each of these applications. Now we have this Q LoRa. So it's just a condensed version of LoRa. Now we have an understanding about encoder only model, decoder only model. We have already seen encoder decoder model. Let's go through this again. Like so, there are some encoder decoder models. So here we'll be having this encoder part, decoder part, and in the decoder part, one extra addition is we have this cross attention. That's all. Yeah, rest all process remains the same. Now let's revise again the things which we have learned so far. So we have seen encoder only model. We understood it is bidirectional. We learn it based on masked language model or next sentence prediction. Then post that we fine tune the head for our own use cases. And the best is understanding the examples of Bert and Roberta. Then we have this decoder only model, which has masked causal attention. And here the task is we try to predict the next token. And how we adapt is we adapt based on prompt, instruction fine tuning, RLHF, LoRa, and all. And this is very good at generation. And the examples are GPT and Llama. We have encoder decoder model, which does both, like bidirectional and causal, which does both, and it's mainly used for denoising. And we adapt it based on text to text fine tuning. And it is best at sequence to sequence to sequence modeling. And the examples are T5 and BART. Right. So now we are at the final part of this sequence learning module. So here we are just looking at a toy example, like what we have learned so far. Some of the few of the concepts in action. So in this particular session, I just want you to show what difference it makes with and without pre-training a model. Like if we are fine-tuning a pre-trained model or tuning a model from scratch, how will the performance be different? So here, for that example, we are taking this open source data, which is called Amazon Polarity. So here, it's customer reviews are there, and Amazon product reviews are there. We just need to label positive or negative on these reviews. It's a simple classification problem. So first step, like as you know, we will be loading the data and visual seeing the some EID exploration on the data. So here you can see it's pretty much a balanced data. So negative samples and positive samples are almost the same. And we can also see the review length, like what are the number of words per review. Right. So as the class is balanced, we don't need to do any class imbalance techniques. So we can go ahead and build the model. Now we need to do tokenization. So right now, as we are using pre-trained model, so whatever model they use to pre-train, will be sticking with the same tokenization. Now we are doing so. We are not doing here some hyperparameter tuning or something. So the objective of this session is not to show all these things. Rather, we'll just see what is going to happen with the same hyperparameter, etc. What is going to happen in a pre-trained, fine-tuning a pre-trained model and training a model from scratch. Yeah. So here, if you see, like in the first session, when I am fine-tuning a model with random weights, like it's not a pre-trained weights. So this is how the performance, like each epoch, you can see the performance starts from 0.52, second epoch, the 0.74. We will see the same for with pre-training also. So in the third epoch, there is a results like 0.76 is what we are getting, and the training will be happening, and we will also see the final results. Now, when we look at that fine-tuning of the model with pre-trained weights, you can see the first epoch itself gave 0.88 results. 0.88 percentage as the, no, it's 88 percentage as the accuracy. So here you can see the difference, right? The moment we used a pre-trained model, which already has an understanding of the language, we just need a single, very fewer epoch. With this particular use case, it happened in one epoch, but there might be some other use case where you might need to train it for few epochs. But compared to training from scratch, you only need very fewer epochs. And even after complete training, you may not be able to reach as good of accuracy as fine-tuning a pre-trained model. Now, if you look at the performance, from scratch, we were getting close to some 70 percentage on test set, and whereas a pre-trained, we are getting 0.88 percentage on the test set. Yeah. Then we can visualize the confusion metrics, etc. So lots of things we can do to analyze the model, etc. This is something which we can do, but this is not the objective of this session. So here, the message which we want to convey here is how better is it to use a pre-trained model. So this is what we'll be using in the future also, right? If you're taking a Llama model or anything, we'll be taking it and we'll be fine-tuning it for our task. So we'll be taking a pre-trained model and fine-tuning it for our task. So with this, we have reached the end of the sequence learning session. Thanks a lot for attending the session.